Good morning, children. So last week we were discussing on one of the effect of light, that is a reflection of light, and we saw in the reflection of light a reflection of light at plane mirrors as well as curved mirrors. Even though we are following the rectilinear propagation of light, which is a basic law of the ray optics or geometrical optics, but that bouncing back of light we are observing in the same medium, means the light was traveling while being incident on the surface as well as while bouncing back with the same speed itself. Of course, velocity depends on the direction, velocity changes, but whereas by magnitude it remains the what? Same. So speed was same. Now this week complete we are going to discuss with a different situation. Again, we are following a rectilinear propagation of light, that light travels in a straight path, but we are going to take two different medium. Means the light is traveling from one optical medium into the what? Another optical medium. What is optical medium and what is opaque medium? Already we have discussed. So opaque medium we dealt with in the last week, whereas this week we are going to go with the optical mediums. So if a light is traveling from one optical medium to another optical medium, we know that it deviates, okay, from its path. So how it deviates? Suppose if you are taking the two optical medium, but they should be homogeneous, okay. So suppose if I take, this is a surface which is separating two different medium, and if I take a light ray is going to be incident at this particular point, let me take it as O point. Now we have taken two different medium, so let me call this as medium 1 and this as medium 2. And in this medium, let its speed be, we are going to take it as the V1, and here we are going to take it as V2 as the speed of light. We know that speed of light changes from one medium to another medium. Okay, that's what all we are going to study in detail today. Now if I take a light ray traveling along this direction, okay, so I am taking a light ray, let me take it as AO is the ray traveling in the first medium along this direction. Now when it enters the next medium, depending on whether optically this is more denser or less denser. So keep in mind, children, the optical density is different from your mass density, okay. So I say it as, when I speak of optical density, when I speak of optical density, we speak in terms of speed of light, okay. Say suppose if I am having speed of light as mho, okay, if I take the speed of light as mho, when I say more, less, these all are what? Comparative terms, okay. So comparative terms. So suppose if I compare with another medium, so if I compare with the, let me take the right now example. If I take the first medium, so in that speed I am going to take it as what? More. So whereas in the second medium, if I take the speed of light as less, okay. So compared to first medium, okay, we are having in the second medium speed of light as what? Less, okay, in these mediums. And what about the optical density then? So if speed of light is more, I say its optical density is less. Okay, and I call it as what? In comparison, I call it as a rarer medium. Okay, in comparison. Whereas the speed of light in the second medium I have taken as what? Less. If the speed of light is less, then I take the optical density of that medium in comparison to this is more. And I say optically more denser compared to the what? First medium. Okay, less denser and more denser. Okay, so this is optical density is what? Its optical density is more, but at the same time you are seeing that its speed is what? Less. So speed and optical density, you can say that they are inversely proportional. You can say. Okay, what you can conclude? The optical density and the speed of light, they are inversely proportional. So today, whatever the points I am going to tell, keep every point in your mind with clear understanding. Okay, because that all basics will help you in solving very simple numericals. Okay, of your MCQs or answering one more theoretical questions. Well, so this is regarding optical density. Now, whenever the optical density is changing, what we are going to observe here is when it enters this particular medium, since I have taken in comparison as per that example, this has a rarer medium and this has what I have taken a denser medium. So obviously we are going to find here is it won't continue in its path. Instead, it is going to what? Bend along this path. So let me take this as OB. Okay. Now, instead of continuing along the same path, what we are saying? It is bending from its path. It is bending from its path. Imagine in the absence of this change of optical medium. So every time I would keep on repeating optical, you have to understand. We are speaking completely. Now onwards, we speak it only transparent mediums. Optical medium which allows the light to propagate through it. Okay. So in the absence of this, or I can say, if the same medium would have continued, the same optical medium would have continued. So let me take the example as suppose if it is, we are having it as air as the example. Okay. And let me take this example as suppose imagine you have the water as the what? Example. Water as the example. And if this is the case, if the change of medium is not there, what would have happened? This ray would have continued in its path, but not continued. Already in the last week, completely I was telling, whenever I would show arrow mark, means we assume would have been, okay? So it is not real, okay? So this would have continued in this path, but now it is traveling practically along this path. Now, this is one situation. Now, in place of this, suppose if I reverse the case, okay, if I am going to reverse the case, if I take another situation, where you are going to observe that light is traveling from say again this is a surface separating two mediums, and imagine here I have the one water trough is there and this is your air medium. So we are reversing the situation. Okay. Now this I am going to take it as medium 1, this I am going to take it as medium 2, and if I select a point of incidence for a ray, this is our normal drop, and if I take the ray here, you can take even at the same angle. Now this is our water medium I said, and this is air medium. Okay, this is air medium. Now when it is traveling from, now water is what? Already we discussed the same combination, children. So this is now more optically denser than this. I can call it as rarer in comparison. Rarer in comparison. Now in this case what we are saying is, if the same light ray is traveling from denser to rarer medium, we are going to observe that it goes away from the norm. It goes away from the norm. Okay. Now again it is, if there is no change of medium, if there is no change of medium would have been there, then light would have continued what? Light would have continued along the same path like this. But now it is practically along the what? Along OB path what you are going to observe. Now observe these both cases. Observe these both cases. What we are saying? Let it be from rarer to denser, or from denser to rarer, optically, okay, optically denser to rarer. But we are seeing that anyhow when there is a change of optical density of the medium, when there is change of optical density of the medium, then we are seeing that its path is changing, okay. This deviation of light, it is getting deviated like this, moving away from the what? Normal. And here it is bending towards the normal. Let it bend towards the normal or let it go away from the normal. So we are going to call this effect or this phenomenon as refraction of light. So what is refraction of light, children? Basically the deviation of light. The deviation of light from its path whenever it travels from one homogeneous optical medium to another optical medium. Okay, is it clear? Again I am repeating. What is refraction of light? The deviation of light from its path when it travels from one homogeneous optical medium to the another homogeneous optical medium. Okay. So why we are referring homogeneous means, don't think, listen carefully, don't think that only like by name it is going to make a difference. Okay, what should be there, A should be there, something like that. Not necessary. Okay, if you take air medium itself, we know that we are having different layers on our along the air column on our Earth's surface, like you are having it as the troposphere, stratosphere, like that. Okay, so if you take different air layers, we know that. Leave that. Okay, stratosphere now. If you take troposphere itself, the first layer on the Earth's surface of your air medium, that density goes on what? Changing. Okay, the optical density goes on, mass density also changes, different matter, but along with that, optical density goes on changing, and because of that, even though the air medium is there, you are having all this as what? Completely air medium itself on your Earth surface. Okay, even though air medium is there, as you go away, it starts becoming what? Rarer and rarer. Here it will be more denser. As you go away from the Earth's surface, as you go away from the, later we study this in detail, okay, in the total internal application and all. So now, just you remember that, don't go with the name, I have taken is completely air medium itself. But even though if I make a light ray to incident like this here, now this ray will keep on moving away. Okay, this keeps on moving away like this. It won't continue the same path. Okay, see the path is like this. But we are having all layers as what? All layers as air itself. Okay, so name of that medium doesn't make any difference for us. What it makes is whether it is homogeneous as an optical medium or not. That makes a difference. So even though it is the same medium, but the moment optical density changes, what happens? The bending of light takes place. Okay, so refraction takes place whenever there is a change of optical density of the medium. Let it be by name different or the same thing but different thing. Okay. Well, so we got what is meant by already refraction of light. A refraction of light, children. Now, let us go for certain terms related to this, same as in case of your reflection you had learned. Okay. This AO ray, I call it as incident ray. So AO is known as what? Let me write everything here. So AO is known as incident ray. Incident ray. Whereas since it's a refraction phenomenon, in the reflection we had called that bounced back ray as what? We had called it as the reflected ray. Similarly, it is a refraction phenomenon. Under the refraction, I call this OB ray as what? A refracted ray. Okay. So we call the OB ray as what? A refracted. Refracted. Okay. According to this term. So refracted. Of course, instead of saying about the normal, that is understood. N dash is what? We are having it as commonly. N dash is what? Normal at the point of incidence. Normal at the point of incidence. Point of incidence. Okay. Well, now apart from this, like in the previous case, you had certain angles. So we had called already this angle as what? Angle made by the incident ray with the normal we had taken as what? It was the angle of incidence. So here also it is known as angle of incidence. Whereas angle made by the refracted ray with the normal, we call it as the angle of refraction. What is the angle of incidence and angle of refraction? And here also same. Angle of incidence, and this is known as the angle of refraction. Okay, clear? Right. So I is what? I is angle of incidence, and R we are having it as angle of refraction. Refraction. Okay, we are having it as angle of refraction. Now apart from this, so this one more surface we are having which is going to separate these two medium, that is xy. Okay, so this is surface. The surface which is going to be what? Which is going to be between your two different optical medium, or which separates two different optical medium. We call it as interface. Maximum we won't refer, but you should know it. Okay, xy is known as what? Interface. Okay, so xy we call it as interface. Now this is regarding the terminology related to your ray diagram in case of refraction of light, children. Now let us come to the conclusions what we are having here. We call them as what? Laws of refraction. Okay, so we are having it as laws of, let me rub here because hope all of you are clear. So AO is what? Incident ray. OB is what? Refracted ray. Let it be here or let it be there. Okay. Whereas N dash we are going to call it as what? The normal at the point of incidence. I is known as angle of incidence. R is known as angle of refraction. So whereas if the light is traveling from rarer to denser, it is bending towards the normal. It is known as what? We are going to observe that it bends towards the normal, whereas if the light is traveling from denser to rarer medium, we are seeing that light goes away from the normal. And this effect of light, whenever it travels from one medium to another medium, that is bending of light when it travels from one homogeneous optical medium to another homogeneous optical medium. We call it as refraction of light. Okay. Hope all the things are clear, children. Now let us come to the laws. Okay. If we come to the laws of refraction, so laws of refraction, laws of refraction. So one of the laws is similar. The first law is similar to your the law of reflection. So what it was saying? What it was saying? Incident ray, a reflected ray, and the normal at the point of incidence lies in the same plane. Here also we are getting the same. That is incident ray AO, a refracted ray OB, and the normal at the point of incidence. All these lies in the plane of the board itself. Already I said what is the meaning of lying in the same plane. Okay. So if you are having incident ray like this and the normal in the same plane of the board, your refracted ray will not come out. Okay. It is also going to be what? In the plane of the board itself. Okay. That itself is first law. Okay. So what it says? Incident ray refracted. What is incident ray we are having here right now? When you are writing statement, don't write AOB like that. Just for reference, I am saying you have to say only incident ray. Okay. So incident ray, refracted ray, that we are having it as OB in both the diagrams, ray diagrams, and the normal at the point of incidence, that is NL dash. All these lies what? In the same way. Okay. Lies in the same way. This is the same plane. Okay. So this is one. Okay. So all these lies in the what? Same plane. So the second law is well, so all these lies in the what? Same thing. Now, what the second law says is, if you are observing here, if I have taken some angle of incidence, we are finding accordingly some angle of refraction. If suppose I change angle of incidence, the angle of refraction also changes. If I increase angle of incidence, remember children, angle of refraction also is going to increase. If I decrease angle of incidence, you are finding that angle of refraction also is going to what? Decrease. Irrespective of whether it is traveling from rarer to denser medium. So let it be from denser to rarer or rarer to denser children. Don't worry about that. Okay. Again, I'm saying let it be rarer to denser or denser to rarer medium. Irrespective of this, what we are going to observe is what? The angle of incidence and angle of refraction are directly proportional. Okay. So when you are seeing, if the angle of incidence increases, angle of refraction also is increasing. If angle of incidence decreases, angle of refraction also is going to what? Decrease. But this ratio, that is sine of angle of incidence. Okay, so what we are having next one is both are directly proportional, and we are having it as sine of angle of incidence and sine of angle of refraction. These both are directly proportional, but this is not the statement. Statement is if both are directly proportional, ultimately that proportionality constant for a given pair of medium is going to remain what? Constant. Okay. So I write as the ratio of sine of statement is, I'll just say the statement, I'll write mathematical statement, ratio of sine of angle of incidence to the sine of angle of refraction. You are writing wordings, children. Okay, statement it is going to always constant. Okay, what the law is saying? The ratio of sine of angle of incidence to the sine of angle of refraction is always constant. So let it be in this case. Okay, the ratio of sine of angle of incidence to the sine of angle of refraction, or let in this case ratio of sine of angle of incidence to the sine of angle of refraction is going to remain what? Constant. Okay, but that constant changes from pair of medium to pair of medium. Okay, the constant is going to change from pair of medium to pair of medium. Not just depends on the pair of medium, even it depends on from which medium it is starting to which medium. Okay, well, so this constant we are going to call it as a refractive index. A refractive index. Okay, which is going to be represented by either you can use mu, it's mu, children. Okay, you can use mu, or you can use n as the notation. Okay, we are using either mu or n as the notation. Okay, but how will you write for these things? Writing is different. Okay, when I take these two, I write here as what, when you take, if the light is traveling from this medium to this medium, then we are going to write as mu of 2 with respect to 1. So I will show you itself. We write as what? A refract index of second medium with respect to first medium. So these notations get used to, or I can write as what? Refract index of second medium with respect to first medium. I said already you can use either mu notation, yeah, mu. Pronunciation is mu. Okay. Well, so refract index of second medium with respect to first medium. Last year already I have come across this notation in the friction syllabus. Okay. So second medium with respect to first medium. But this mentioning of refract index of second medium with respect to first medium is going to be different when you refer different texts. Okay. So, but all the things are valid. See, I can write it as like this, or I can write the same thing as mu of 2 with respect to 1 like this, or I can write as even mu of 2 with respect to 1. Okay, so all these things are valid, children, and even you can write mu of 2 with respect to 1. Okay, so all these things are valid. So you can use any notation. Usually we go with either this or your NCERT has given this notation. Okay, even they might have used n to 1 or mu to 1, but they write subscripts like this. But let us go with this, we feel comfortable. So refract index of second medium with respect to first medium. So okay, we are going to read like this. Hope reading is clear. How will you read this? How will you read, children? A refractive index. Short form is valid. Refractive index, short form is a valid short form. You can use in your notes. Okay. Refractive index of, I say as second medium with respect to what? First medium. First medium. Hope it is clear, children. Refractive index of second medium with respect to what we are having? First medium. Okay. But do remember, The refract index of second medium with respect to first medium is not equal to first medium with respect to second medium. Okay, don't write that. Refract index of second medium with respect to first medium is not equal to refract index of first medium with respect to second medium, because here we have taken the same pair, that is air and water and water and air. Okay, but refract index of second medium with respect to first medium becomes what? Air with respect to water. But here water with respect to air. So it changes. Okay. So always when you say it as refract index of second medium with respect to first medium we take it as what? The incident ray medium. Okay. We call it as what? Incident ray medium. This is refracted ray medium. Okay. So if you take this medium, okay, and this medium. So here we are going to read as refract index of air with respect to water. But here I read as refract index of water with respect to air, and both are not going to be equal. Okay, real. Okay, it changes. But all the things are clear. I hope these are the laws we are having, and this ratio remains always constant. We call this constant itself as what? Refract index. Now, one more interesting thing is, before we are speaking of optical density, okay? We are speaking of optical density. Now, if you take optical density and refract index, both are directly proportional. Optical density is directly proportional to what? Refractive index. Means more the refractive index, it is optically more denser. Less the refract index of, okay, any one given medium, then it should be what? Less optically denser. More the refract index, since more is the optical density, speed is what? Speed of light is less. Means if I have more refract index medium, in that speed of light is less. Less refract index medium, speed of light is more. So, but these two are directly proportional, and both of them are what? Now it's clear. Inversely proportional to what? Our speed of light. Speed of light. Hope everything is clear, children. Have a glance. Well, children. So we defined refraction of light, and we saw the terminology related to that as well as the laws of refraction. In that, one of the law, what it was? It was ratio of sine of angle of incidence to the sine of angle of refraction is going to remain constant, and we call that as what? Refract index of second medium with respect to first medium. Okay. This was the thing. Now, if I take a situation instead of oblique incidence. So what we took in both the cases, we have taken oblique incidence. Okay. So instead of oblique incidence, if suppose I am going to take the ray being incident along the normal itself. If I am taking the ray is going to be incident what? Along the normal itself. Now what happens to your angle of incidence is? Angle of incidence is what? 0. Let me take this medium as again medium 1 and this is medium 2 you are having. Medium 2. Let us take in this the speed of light as v2, in this the speed of light as v1. Okay, these are the speeds of light. So angle of incidence is what? 0. Then as per this, what should happen to your angle of refraction also? 0. Okay, so we are going to see that the light is going to travel without any deviation. Without any deviation in its path. Does it mean that it is not refracted? No, it is refracted. Okay, it is refracted, but we are saying that its path is not changed. Okay, we call it as normal incidence. Okay, so when the ray is incident along the normal, that is for the normal incidence, what we are finding? Angle of incidence equal to 0, angle of refraction equal to 0. Actually, now listen the point carefully. Actually, this thing was mathematically proved. Okay, mathematically. It's only theoretical. Okay, so theoretically proved by the scientist named Fermat. Okay, by the scientist named Fermat. I'll come to that. His principle. We have a very interesting or most required. Okay, principle known as Fermat's principle, which is required to know that after all why light deviates from its path. Okay, why light deviates in its path from its path when it travels from one medium to another medium. Not only here, even we have seen that in the reflection of the light was deviating only. We calculate even angle of deviation as what? 180 minus the 2 times angle of incidence or 2 times angle of refraction. We have to calculate it. Okay. There also light was what? Deviating. Hope you could remember. If this is your mirror laser, so the incident light was bouncing back what? Into the same medium. Into the same medium, and how much it got? If this is angle of incidence, and both are same itself for us. So how much it got deviated? We had calculated this much. Means the deviation was there also. Deviation is here also. Then the question comes: why deviates from its path? And that was explained by the Fermat. We call it as Fermat's principle. Okay, we'll discuss that afterwards. Okay, and right now. This theoretically was, I was on the point, this theoretically was given by Fermat, okay, scientist Fermat, whereas practically, experimentally, okay, so this is theoretically given by Fermat, whereas experimentally it was proved. Experimentally it was proved by another scientist by name Snell, okay, by name Snell. Hence, it is also known as the second law of your refraction is also known as what? Snell's law. We call it as even Snell's law. Okay, then what Snell's law says, children? The ratio of sine of angle of incidence to the sine of angle of refraction for a given pair of medium is going to be what? Same. Okay, or of a given medium is going to be what? Same. Whereas it changes if I change the pair of the medium again, okay? And is going to what? Constant, he said, and that law itself we have called as what? Snell's law. I can call it as Snell's equation also, okay? Now if you take this, if you apply that equation, Snell's law here, if you apply Snell's law here, what happens then? We are going to get applying Snell's law, if I apply this Snell's law here, since angle of incidence equal to 0 and angle of refraction is also equal to 0, so 0 by 0 is what? Undefinable one thing, and we are going to get, suppose refractive index is 0 also if I take, that is meaningless because every medium has its what? Some refractive index. Say suppose if I take even the vacuum refractive index, we are having absolute refractive index. I speak about that is going to be equal to 1. Okay. Absolute refractive index of vacuum is going to be equal to how much, children? 1. So obviously every medium has some optical density. Some optical density. Hence, in this case, Snell's law fails. Okay. This fails. When it fails, children, it fails for the normal incidence or when angle of incidence equal to 0. Okay. When angle of incidence equal to 0 or for the normal incidence, Snell's law fails. One question comes for you in the theory as well as the objective for 1 mark. But in the objective depends on your exam, JW exam, or you are writing NEET exam, or you are writing your CET, Karnataka CET exam, differs. Okay. Well, question is, when does Snell's law fails? So your answer can be what? Or your option can be what? For the normal incidence or for the angle of incidence equal to 0. So remember this important point. Okay, now let us come here. When, if suppose this cannot be 0, as every medium, including even your vacuum, free space, is having some optical density. Then how will you define it? Because before, as per the law or as per Snell's law, we will define it as what? I can define it as refractive index of second medium with respect to first medium as what? The ratio of sine of angle of incidence to the sine of angle of refraction. But now we cannot define that. Now we are going to define in terms of speed of the light. Okay, we define when Snell's law fails. So we are going to define even actually the new one in terms of velocity. Okay, we are going to prove it in wave optics later using wave theory. Okay, wave front theory. So we are defining now. We are defining the same refractive index of second medium with respect to first medium as what? Ratio of speed of light in the first medium to the ratio, to the speed of light in the what? Second medium. Okay, so we have it as what? Ratio of sine of angle of incidence to the sine of angle of refraction, but sometimes that may fail. So, but this is evergreen. Okay, so what I can define as refractive index of second medium with respect to first medium, I can take it as always as what? Ratio of speed of light in the first medium to the speed of light in the second medium. Okay, hope you everyone got it. Now, here we are going to define different refractive indices. Okay, if suppose I'm having any medium, let it be. But if I'm having the first medium as say vacuum, even we can take it as A, but theoretical is actually vacuum. Practically, since refractive index of air is going to be very close to refractive index of the vacuum. That is, refractive index of air is going to be around 1.0003, whereas refractive index of vacuum or free space, we have it as 1. Remember these data, children. Refractive index of vacuum or free space is what? 1. But that of air is what? 1.0003. Since a small difference is there, we take both granted, okay, while working the mathematical part. So refractive index of any medium, if I am writing with respect to vacuum, how will you write? Second medium with respect to first medium. Which is your first medium now? This is your first medium. This is your second medium. Okay, so how will you write this one then? Speed of light in the first medium. Speed of light in the first medium is what? Vacuum. Speed in the vacuum is represented by what? C. How much it is? 2.9979, okay, some 4 more digits will come into 10 to power of you are having 8. But we take approximately as what? 3 into 10 to power of 8 meters per second. Both in vacuum as well as air, okay. So divided by speed of light in the medium. So what we are having? I can write like this. Now what I have taken first medium as? Now listen carefully. First medium I have taken as vacuum, or I said even you can take it as air also. But second medium is apart from air and vacuum. Okay. So what we are having? Second medium must be what? Apart from air or vacuum. Air and vacuum. Air and vacuum. Okay, hope it's clear. Apart from air and vacuum. Now in this case, we call this refractive index. I can write only as mu of medium. I can write as what? Mu of medium. Node of indicating here as vacuum is there, air is there. I not write like this. Air is there or vacuum is there. So without this I can write. Okay. Without this I can write. Okay. So now this is known as absolute refractive index. We call this what? Absolute refractive index. Okay, what is absolute refractive index? Refractive index of any medium. Refractive index of any medium apart from the air or vacuum with respect to what? Air or vacuum. I'll just say this part you remember. I can set as what? What is absolute refractive index? Refractive index of any medium with respect to air or vacuum. We call it as what? The absolute refractive index. Say for example, refractive index of if you take glass. If I write only like this, it indicates what? Now first medium we are having is what? Air or vacuum. Remember, here what we are having? Air or vacuum. So refractive index of glass we are having it as 3/2 or you can take it as 1.5. Okay. Unitless because it is unitless. Okay. This is not having mu is what? It is not having any unit. No unit. Dimensionless, unitless. Okay. Because speed by speed or sine of angle by sine of angle. Okay. That becomes what? Only the number. Okay. So ultimately here also units are going to cancel. So it is not having a unit. Unitless it is. And now we are getting it as what? 3/2 is 1.5. No unit. Similarly, refractive index of if I take water, that is going to be what? We have it as 4/3, or you can take 1.3. But these values are going to be what? Taken as on average or standard values whenever they won't mention refractive index of that glass or refractive index of water, because water maybe what? More optically denser, little less optically denser. Depends on because we have a different type of water. Okay. Similarly, glass water. Glass also we are having different. So suppose if you are having the more denser, its value may be 1.6, 1.78, something like that. But if I am having water also what? It may vary 1.33, 1.36, anything may be there. But do remember, these two standard values you have to remember while solving objective questions and all. Because whenever they are not given, you can take standard, of course. If they are not questioning you to determine them itself, okay, in that case, you can take these standard values, okay. And apart from that, better you remember these things also. Then, which is having the least refractive index? Free space. 1, okay, means apart from free space is what? It is not with any medium. So just if you take any medium, then its refractive index what? Is going to be greater than 1, including air, because air also what we are having 1.0003. Okay. So refractive index of vacuum is what? Then minimum. And that is equal to what? 1 we are having. Whereas refractive index of any other medium when you start taking, it goes on increasing. Again I am repeating this point. When you take refractive index of any other medium, it goes on increasing. Even like if you take your diamond and all, we are having up to 2.4 at all. Okay, diamond is having its absolute refractive index as what with respect to air or vacuum as what 2.4. Okay, then what does it mean? Even we can extract from this the other understanding also. I'll give an example here. See, let me give you one example. If I write a refractive index of suppose glass, just know what I have written. I have written as 1.5. But the same thing I can write as what? Speed of light in vacuum divided by speed of light in glass. Okay? Speed of light in glass becomes what? Speed of light in glass, this is GR units for glass. Okay? So, for glass medium. Okay? So, speed of light in glass becomes what? That becomes C divided by refractive index of glass, mu of glass. Now, what I said just now, I was stressing so much on that point because of this one. What I said, refractive index of any medium when you take, compared to free space, it goes on what? Increasing and is going to be more than 1. Okay. So only for the free space we are having it as 1. Whereas for other things, okay, we have taken that as a standard 1, okay. So, and remaining, we in comparison we go on right. So we are having it as more than 1. And then mu of glass, just to have given the example, how much it was if I take standard value also, how much we are having? We are having it as the 3 by 2, or I can write, since it is in the denominator, I can write as 2 by 3 times of C. Then what that indicates? Velocity of light. Okay, velocity of light or speed of light in the glass medium we are having is what? 2/3 of speed of light in what? Free space. Means when the light enters from free space into any other medium, it goes on what? Decreasing. And what is this 2/3? Or I can write this as it is 1 divided by 3 by 2. Or here it is. Okay. This is the fact you have to understand. What this is saying, I can see the way of writing. Way of understanding makes a lot of difference. Okay. What I can write now? I can write the same thing in different way. Right? Okay. I write as 1 divided by, same as that. 1 divided by mu of glass into CL. One and the same? One and the same, children? Okay. So what happened to speed of light then? It became 1 by mu times of that medium, okay, compared to what? Free space. So what I can call mu as? It is the factor, okay, what we are saying? The speed of light reduced to what? Refractive index times of that particular medium, okay? Right. So mu is the refractive index of, absolute refractive index of glass you are having. So I can call it as what? It is a factor which tells you that how many times the speed of light is reducing, okay? Reducing in that particular medium compared to what? Free space. For example, if I say the same thing glass now in different way, see the way of predicting is, understanding differs, okay? If I say it as refractive index of glass is given as 1.5, then you'll understand, okay? So what will make quickly, okay, flow should come to your mind is what? Thought should come to your mind is, the speed of light in glass is 1 divided by 1.5 times of speed of light in the air or vacuum. Clear? Or quickly you can calculate as what? 3 into 10 to the power of 8 divided by 1.5. That becomes your speed of light in the what? Light in the glass medium. Okay, everyone is clear? Well, so we are discussing about absolute refractive index. If I write like this indicates the other side medium, because our general notation is what? Second medium with respect to first medium. If I write only subscript of second medium, not the superscript of the other medium. That indicates what? I'm speaking of absolute refractive index. Then I am stressing on this. Certainly there must be one more refractive index, which is nothing but taking two different medium apart from the air or vacuum. Okay. Is it? Okay. So the same normal instance, if I take instead of air, if I take both of them different mediums, say let me take it as this is the water medium and this is the glass medium. Okay, I am taking the water and glass medium. So both of them are apart from your air or vacuum. Okay. If I take in this case, if I write the same relations, well, see, let me take the refractive index of second medium with respect to first medium. How will you write down? So I'll write a refractive index of second medium with respect to first medium. Okay. We'll write as what? Refractive index of which is our second medium? Glass. So I'll write as glass here. Okay. So which is our first medium we are having? Water. So I'll write as water. Okay. Because your incident is in this medium. Now how will you write this one? If suppose speed of light in the water medium, if I take it as VW, and speed of light in this medium I take it as VG. Okay. So these are the what? Speed of light in the water medium and speed of light in the glass medium. Then what is your definition in terms of speed of light? It's nothing but ratio of speed of light in the first medium to the what? Speed of light to the second medium. Just now we discussed that only. Then I can write as VW divided by what? Agreed all of you? Now the same thing what I do is I'll multiply and divide by the C. I'll rewrite the same thing as I can write as VC divided by VG divided by VC divided by VW. Okay, so this is the denominator itself. This in the super denominator it comes to what? Numerator. So just what are the multiplied and divided by the what? C. Okay. Is there any problem? It's clear I hope. Nothing at all, just alter the equation. But if I write like this, what this indicates? So take this side and take two more diagrams this side. Okay. Now I am taking two different situations here. This is air medium or vacuum medium we can take, and this I have taken as water medium. Okay. Here the ray is incident along the normal and goes undeviated. The speed of light here is what c is the speed of light here I take as v. Similarly, I have taken one more situation here, and why I have taken different is because you should not think only for the normal incidence we have this ratio. So since this remains the same, it's independent of in what direction the ray is incident, because already what the law says, second law, the ratio of sine of angle of incidence with the sine of angle of refraction is a constant. Means it depends only on the pair of medium and from which medium to which medium light is traveling, whether glass to water or water to glass. Because I said they are not equal, they will be different. If light travels from glass to water is different, at the same angle, water to glass is different. Okay. So it depends only on the pair of medium and the ray is traveling from which medium to which medium. Okay. And of course, it depends on temperature and all those things we can learn later. Well, now I have taken one more. So imagine this is again your air medium is there or the vacuum is there. At some angle, the ray is incident and it is getting refracted into the glass medium. And here speed of light is once again c. Here speed of light I take it as v. Now in this case, if I ask you to write, the okay. So how will you write this refract index of absolute refract index of glass children? You write as c divided by what? C divided by write as velocity of light in the this water is there, okay? So velocity of light in the water. Similarly, if I ask you to write in this case absolute refract index of glass, how will you write? Speed of light in the first medium by speed of light in the second medium. You write like this. But what these are? These are your absolute refractive indices. These are your absolute refractive indices. So same thing you are having here also. What you are having? This is what? This is nothing but refract when it is absolute. Listen. When it is absolute refractive index, no doubt saying every time that it is absolute refractive index. Okay, I can say it as only refractive index of glass. When I say only refractive index of glass, you have to understand with respect to what? Air or vacuum. Okay. So otherwise I mentioned refractive index of glass with water, refractive index of glass with some particular helium, medium, something like that. Okay. So we are having it as what then? This is nothing but we are having refractive index of glass. So I can write as refractive index of glass. What about this? This is nothing but we have it as the refractive index of water. So I write as refractive index of water. Now this is one more relation what you are getting. Relating what? Relating this term with their absolute refractive indices, and this term is known as relative refractive index. What do we call this one? Relative refractive index. Okay. So relative refractive index of glass with respect to what? Water. How you can write this as in terms of their absolute refractive index, you are writing as what? Glass by water. Glass is water, second medium. Water is water, first medium. So then what I can generalize to them, okay? I can write generalized equation as a refractive index of, or I'll write here. I'll run this. Hope everyone is clear what we did, okay? Because even you get the lot of drawing these many diagrams. You get one of the question for 2 marks to get the relation between relative refractive index and the absolute refractive index. How will you define relative refractive index? A relative refractive index of a medium with respect to what? Another medium, but that medium should not be what? Air or vacuum, otherwise it will become absolute, okay? Because here if I won't write meaning anything is what? Air is there or vacuum is there, okay? So clearly you have to mention refractive index of a medium, optical medium, with respect to another medium apart from air or vacuum. Apart from air or vacuum is known as what? Relative refractive index. And instead of drawing these diagrams, just you can write directly identical things in your derivation. Okay. So this comes as a relation between relative refractive index and the absolute refractive index. After completing taking example, you can generalize it as, so in general, what I can write? In general, I can write as the refractive index of second medium with respect to first medium dot, because second came in the numerator, first came in the denominator. So absolute refractive index of second medium is other medium is what? Air. Absolute refractive index of first medium. So I was saying you before that if I take refractive index of second medium with respect to first medium is not equal to what? Refractive index of first medium with respect to second medium. Okay. So when light, that indicates what? That indicates in your Snell's law that constant changes depending on light is traveling from first medium to second medium or second medium to first medium. That is how practical here. Suppose if I write refractive index of glass with respect to water, this becomes what? Glass by water. Just know I have given standard value. Refractive index of glass is how much here? 3 by 2 is the. Of water, what I said? 4 by 3 is the. Then this becomes how much? 9 divided by 8. Right? What this indicates here? Light is traveling from water to glass. But suppose if I take reverse, what happens? Refractive index of, if I write water with respect to glass, meaning here is what? Light is traveling from glass to water. In this case, it becomes what? Second medium should the numerator, second I should write, okay? Second medium with respect to first medium. So refractive index of water by refractive index of glass. Refractive index of water is how much? 4 by 3. Glass is how much? 3 by 2. See, it is 8 by 9. Or you can conclude what? It has become reciprocal. What you can conclude then? So this implies that refractive index of second medium with respect to first medium is what? Reciprocal of refractive index of first medium with respect to second medium. As well as they are not equal. Second medium with respect to first medium is not equal to first medium equal to second. So remember every point. Okay, so this is our general equation. Okay, and when I take without any one more the superscript, what that indicates? That indicates that we are having is air or vacuum is the balance. And this is known as what? Relative refractive index. When I say relative refractive index, this should not be air or vacuum. You are going to have children. This should not be air or vacuum. And we are going to have the refractive index of second medium with respect to first medium is not equal to first medium with respect to second medium. But we proved that refractive index of second medium with respect to first medium is what? Reciprocal of first medium with respect to second medium. Okay, hope all the things are perfect and clear. Have a glance once. Understand? The relative is what? Absolute is what? Hope everything is clear. Now let us have one more part here. We saw very clearly speed of light. Speed of light is what? Is maximum in the vacuum. Next comes is your air. Next depends on the what other mediums you are going to select. Okay. Now apart from this, speed changes, but when the light travels from one medium to other medium, Speed is anyhow changing. Apart from that, even its wavelength changes. Okay. When light travels from one medium to another medium, the XY interface and your n dash is your normal. When the light travels from one medium to other medium, so what we observe already? So one thing is when it travels from one medium to travels from one medium to another medium, so obviously speed is going to what? Change. Speed changes, and how it changes depends from where to where it is traveling. Okay, if it is traveling from rarer optical, keep parallel in the mind is not mass density. Okay, optical density. Okay, if optically it is traveling from rarer to denser medium, speed is going to decrease. If it is traveling optically from denser to rarer medium, it is going to what? Increase. Like air to water, speed decreases. But if glass to water, speed is going to what? Increase, because optically compared to glass, water is rarer medium. Okay. So it is going to change. But how it changes depends on the pair of the medium. Okay. Or you can say depends on the refractive index. If refractive index is more in the second medium, speed is going to decrease. If refractive index is less, speed is going to what? Increase. Okay, that here you have made already the relation between optical density, speed, and what? The refractive index. Whereas not only the speed, even we are going to observe is the wavelength also changes. Wavelength also changes. But frequency of that light is not changing. Okay, so frequency is going to remain constant. Frequency will not change. Will not change. Now let us give you one more relation quickly for you children. Suppose speed of light here is v1 here. Let me take this as the first medium, this as the second medium. Okay, and if speed of light is v1 and here the speed of light I take it as v2 and here as v1, let the wavelength of light traveling in this medium be what? Lambda 1. Let it be here lambda 2. It will be represented by lambda. But I said frequency will not change. So frequency is going to remain what? Same. No f1, no f. Okay, frequency remains what? Same itself. Okay, now how will you write your relative refractive index? So in this case, I will write relative refractive index of second medium with respect to first medium. Let us sum up all the relations what we had, children. Let me take as I1. Sorry, only I is not. And this as R, angle of refraction. So first initial, let us start with the from beginning knowledge what we had. Initially, as per the laws, we wrote as sine of angle of incidence to the sine of angle of refraction. When for the normal incidence, this is Snell's law of field, we call it as Snell's law. What we wrote? We wrote as the v1 by v2, speed of light in the first medium to the speed of light in the second medium, e1. This just now we wrote as what? In terms of absolute refract indices, the same refract index of second medium with respect to first medium, we got as the ratio of absolute refract index of second medium to the what? First medium. Okay. Now, but we know in the first year you have learned speed of light in terms of frequency and wavelength or speed of sound you have learned. What is the same for the wave nature? So we have the relation what? F lambda. Then I can write that in terms of what? F lambda. But F is not changing. But wavelength in the first medium we are having is what? Lambda. Whereas here I can write again F is not changing. Whereas wavelength is what? Lambda 2. Lambda. Then F is going to get cancelled. So hence what I can write only? I can write as only lambda 1 by lambda 2. Okay, so this is one more ratio. Hope it's clear. F I am cancelling. I have shown already why it comes. I can write like this. Now, this gives you one more idea. Now let us take absolute refract index example once again. If I write refract index of glass, if I write only like this, already just now we discussed what it indicates. Only refract index of glass I am speaking. Means other medium is what? Always two medium are required. Okay. But other medium indicates what? That is nothing but is indicating what? Other medium is air is there or vacuum is there. Now how you have written this one as? This I can write as what? Then first medium becomes what? Air. So wavelength in air or vacuum divided by wavelength in the what? Glass. Then wavelength in the glass becomes what? Wavelength in the glass becomes what? Wavelength in the air or vacuum. You can take air or vacuum children. Air or vacuum divided by refract index of glass. But refract index of glass is what? 1.5 is what you got. You got that wavelength in the glass medium is 2/3 of wavelength in the what? Air. What you are observing, one more conclusion here. When light travels from free space or air to any other optical medium, its wavelength is going to what? Decrease. Its wavelength is going to decrease. Hope it's clear. All of you please today once again, even though you may be live, but still once again observe each and every point or make a note yourself. Okay, once again try to recall yourself because many conclusions we have made. Tomorrow yet to make some more conclusions in terms of your optical path and all. So even we'll prove tomorrow using Fermat's principle, important one, okay, basic understanding that why light deviates. So tomorrow also it's going to be interesting to know that why refraction of light or reflection of light after all takes place. Well, children, thank you for joining. Good day.